Hello, can you hear me? So the people on Zoom cannot hear anything. There's no sound. And it's not me, not just me, it's several people.
Are you able to hear me?
Yes, now yes. Now yes.
So I'm sorry for that. There is some fancy interrelationship of the signal at different times, which is quite more interesting than just doing the same thing at different times. So what is a traditional way of nonlinear time series analysis? I think there are two main streams. One is related to information theory, like mutual information, and then you have test against some surrogate data representing the null hypothesis. I will come back to that surrogate data a little later. Another way is to reconstruct the phase space. And that is somehow quite attractive, because if I have knowledge about the phase space structure, I have the maximum possible knowledge about the dynamics of the system. And that would be very nice. I mean, then I could maybe predict, I could extract several features, interesting features from that. So that seems to be a very attractive way for doing that. But usually, one do not has, well, you can characterize a dimension. You may predict the Lyapunov exponent in order to know whether you have chaotic or regular dynamics, or you may also derive measures like nonlinear interdependence, where you are evaluating if there is some generalized synchronization between two dynamical systems, etc. So if we could have access to the phase space, that would be really an attractive thing. But we have not a direct access to the phase space. We only account for time series measurement, and time series measurements means a projection on phase space. Usually, if we are measuring just one quantity, then we are projecting in a possibly high-dimensional space on a one-dimensional manifold, and that means a measurement, right? The question is whether we are able to reconstruct something similar as the true phase space, and the answer gave Tuckens decades ago, and the answer is yes. So if we are staying with my harmonic oscillator as the most simple system, we can put two dots, a red and a green dot, on the time series, and we can interpret them as two components of a bidimensional vector. So we have a red axis and a blue axis, and then we can shift those dots along the time series, and what we are recovering in that case is a perfect reconstruction of the attractor. Well, that is somehow a little bit cheating, because I know beforehand how many dots I have to put, and I know the optimal distance between the dots I have to put there. Here's another example of the Rossler system, which you know for sure, and some embedding, some reconstruction of the phase space. We can see geometrically they are different things, but topologically they are equivalent. So there is a smooth invertible map which transports one figure to the other, and if we are calculating some or whatever quantity from the violet or the red object, we will get the same result. So that is equivalent, let's say topologically equivalent. That's very nice. But what if we have an inadequate number of those dots? Let's say if we have if the embedding dimension is too large, well, that doesn't matter if you have enough data. I mean, if you have the larger the phase space, the less is the density of dots which we are reconstructing, and probably we need a longer stationary time series in order to reconstruct. But in principle, it doesn't matter. So we will get the correct answer again. So here we can see a four-dimensional reconstruction. It's a projection on 3 dimensions over there. So that doesn't matter too much. But what if the dimension is too small? here I have a two-dimensional reconstruction that leads us to false nearest neighbors. I mean, dots which are neighbors here in this representation get distant if you are increasing successively the embedding dimension, and that can be captured by the rate of false nearest neighbors. Applying this formula, again, there has to adjust a parameter. So there's already 3 parameters which are involved: the embedding dimension, the distance between the dots, and the false nearest neighbor rate, which is quite a delicate issue. But in principle, that works. In principle, that leads us to the correct answer. What happens when the time lag is too small? In principle, it doesn't matter, but it is inconvenient, especially if you have some noise in the data. Then we do not have this very nice, the dots following that nicely this closed curve, but then they are dispersed somewhere around. And if you have too many autocorrelations, then like in that case here, we are not able to resolve the structure which we are interested in. So that is not convenient. Typically, one uses the autocorrelation length or the mutual information and the mutual information length in order to have an estimate about the time lag for the phase space reconstruction. And noise, well, noise is poison. I mean, if I would like to evaluate the structure, I feel again a reconstruction of the Ressler system. I think there is 1 or 2% of noise. I mean, the variance of noise I put it upon is about 1% or 2% of the variance of the Ressler oscillations in the X or Y coordinate. So the structure is destroyed. I mean, that is really poison for what we are doing, and so we have to take care. So what one can say is that in principle it's very nice. This Tucken's theorem is a beautiful thing, and it has been applied very successfully to different kind of complex systems, and they derive very beautiful results from that. But in principle, you need stationary, low-dimensional systems with a very, very low noise level in order to get out something reasonable from this kind of procedure. And well, I like very much this book from Holger Kanz and Thomas Schreiber, Nonlinear Time Series Analysis, with a lot of examples, very nice explanations. I like that book, and they also provide a software package, a TCN time series analysis, it's called, free available from the Max Planck Institute. So I can recommend this literature. So that was data pre-processing. We are reconstructing phase space, and then we have some object, and now the data analysis starts. We would like to evaluate the topological structure. Maybe somebody is interested in the dimension of this subject, or Lyapunov exponent, or whatever, right? And of course, we will get something out numerically. I mean, if I feed up my computer with numbers, I will get out numbers. I'm able to make a figure, and it is not clear whether these numbers have any kind of meaning, right? So one has to test, make some significance tests. One usually tests against some null hypothesis, and the null hypothesis usually is to create data which share the same linear properties than the original data, but they are noise data. I mean, there's no phase-space structure. If you make some phase-space reconstruction, it will be diffuse cloud of dots over there. There's no real phase-space structure which we are able to resolve. And typically, they are using Fourier transform surrogates. So the idea is that we are making a Fourier transform of the signal we are going to analyze. We get the Fourier amplitudes and phases, and then phases are replaced by identically independent random numbers uniformly distributed against 0 and 2 pi. By that procedure, all deterministic structure is destroyed, and we will have noise with the same linear properties, with the same power spectral density, making a back transform, and then we see, well, that are Fourier transform surrogates, this in this first iteration over there. But if we are looking a little bit more careful to this data, we can see that the amplitude distribution in the time domain differs from that of the original signal, and that might be dangerous. I mean, if you have a complex system where you are measuring some univariate quantity, usually you may expect, because of the central limit theorem, that the distribution of dots or of a signal in time domain is a Gaussian, and a nonlinear measurement function may distort this. They could make some deformations from that. So if you're destroying the amplitude distribution in the time domain, that may lead to false positive, right? So in the next step, the people are adjusting the amplitude distribution in the time domain. That causes, again, deformations of the power spectral density, and one tries to do that in an iterative manner up to some precision, which one is able to define according to the situation he's confronting. Well, the point is that nobody assures, there's no theorem that assures here that this procedure converges. So typically, after 400 or 500 iteration steps, if this accuracy condition is not fulfilled, one starts again with a new seed, and praying that everything works well. Okay, but let's assume that everything works well, and we could use these kind of surrogate data in order to compare what is going on. Well, I will shortly demonstrate a little bit how to make such a kind of analysis. For example, estimating the dimension of the object. What is usually well, there are different kind of dimensions one might calculate. One very popular one is the box counting method, using for that. And so what one is doing is looking for a scaling of objects covering the object you are interested in, and looking how is the number of objects scales with the extension, with the size of them. So that is the usual way how one estimates the dimension. Here is a two-dimensional one, the Koch curve on the right-hand side, and that works very well in the limit of infinite objects of size tending to 0. But we do not have the object. We do just have a distribution of dots in this reconstructed phase space, right? We do not have the complete attractor because our experimental setup works with some recording frequency. So we have some discrete finite number of dots in phase space. But you may imagine that we do not have the square, just a homogeneous distribution of dots over that square. And then we can see, if we are dividing this, the fraction of dots which are decaying on the average on regions of size epsilon provides the same scaling procedure, so that we can use this, and usually one is calculating the fraction of dots in the reconstructed phase space which are decaying in the vicinity of size epsilon, and then one is looking for scaling of this correlation sum, it is called, as a function of epsilon. That is the procedure one is doing. So one expects that at least for a certain range of epsilon, this correlation sum is proportional to e to the dimension of the object. So one can see here again the example of the laser that is extracted from the book I recommended a few minutes ago. That are different embedding dimensions, low embedding dimension, and then it increases over to the right. And then one is looking where for different embeddings over a certain size of epsilon, we have some power law. I mean, some straight line in a double logarithmic plot. And the slope of that would be the estimate for the dimension. So one is looking for the logarithmic derivative of that is drawn here. Again, one is looking for a certain region where the estimates for different embedding dimensions and for at least a long enough range, let's say, for varying epsilon, one will have the same estimate for the dimension of the object. That is the idea. Of course, if the range is too large, one cannot expect any reasonable results. If it's too small, noise will come to the business, and that increases the numerical estimates. Noise would have estimate infinity. All right. So that is the idea, and as I said, it has been applied to many examples, and I think people have published excellent results doing these or similar things without any question, right? However, one has to take care. There are several parameters which has to be adjusted, and straight lines. I mean, there are people which are seeing straight lines in any figure, so one has to be caution. And one publication in '98 that was published in Neuroscience Letters, they did some phase-space reconstruction of intracranial data of epileptic patients, and they saw a strong correlation of the estimated dimension with the beta of the power spectrum, with the slope of the power spectrum. It means that the autocorrelation, linear autocorrelation, comes into this business, and it is strongly correlated with -0.8 nearly. So that is certainly not what one is looking for, a complicated estimator for the autocorrelation length. That is not convenient. I would like to show one or two more examples. Here we have a random walk, the position of the walker in n+1 steps is the position after n steps plus a step, and the step is a Gaussian step, a one-dimensional random walk, and the time series looks like that. I mean, it's Brownian noise, right? So we have Brownian noise here. We have this, that is a power spectral density of this data after 4 million steps around. And we can see how it deviates from the zero position, somewhat counterintuitive, but that is due to the strong autocorrelations in this data over there, right? And if we are doing some phase-space reconstruction from this noise, we will have a saturation plot of that type. And what we can see is very nicely that the range where for different embeddings we encounter nearly the same estimate, and the estimate will be equal to 1. I mean, that is like in a textbook, right? I mean, you have a very broad range of almost constant estimates and nearly independent of the embedding dimension. But the estimate is certainly wrong. I mean, the true dimension should be infinity, right? But this is provoked by this very strong autocorrelation. So if we are extracting low frequency components and taking a time series which is sufficiently long, that should be lifted, right? That should be changed, and that is what we did in the next figure. So that is what was the original one. Here, the filtered one, where we extracted the low frequency components. And we can see for embedding dimension 1, the estimate is 1, 2 will be 2, 3, 4. If you have 1,000 and enough data, we could produce enough data, the estimate would be 1,000, as it should be. There's another example from, again, with epileptic seizures. Here you can see the electroencephalograms. And that was produced, I had some sabbatical in the Max Planck together with Holger Kanz over there. And there came some high school student, and they could improve their qualification in school if they make some small research project with somebody at the university. And he was looking to make something on nonlinear dynamics and brain dynamics and these kind of things. So I told him all these, what I told you in several sessions, and he analyzed this kind of data in a similar way where other groups did it with intracranial data, publishing it in physical review letters in Nature, etc. So that are saturation plots from this data that is in the pre-ictal period, during seizure, after seizure, and we can see that we encounter some region of epsilon where we get some nearly independent result for the estimation of the dimension. And it is also nearly independent from the embedding dimension which we applied. So with a running window approach, we estimated the correlation dimension of the brain dynamics, and that is the result. So that is the pre-seizure period. After 10 minutes, the seizure starts in this recording over there. Then we got a strong drop of the estimates of the correlation dimension, and then more or less strong fluctuations in the post-seizure period over there. And then I asked this boy if he thinks that is something significant. And he gave me, to my mind, a very intelligent answer. He said, well, you see, before seizure, there are some fluctuations which are comparably small. After seizure, the fluctuations increases, but by no means they are on the size of this drop, which you can see during seizure. Beside of that, seizure is known as a hypersynchronous state, dynamical state. So in phase space, I would expect that there's a collapse. It's getting very, very simple dynamics, simple correlated or highly synchronized dynamics. So it is reasonable on one hand and has nothing to do with it before or after seizure. I think that is significant. And then we did the same with the surrogate data, which I explained some minutes ago, and we got out that. I mean, that is just the result by Pereira. The results are highly influenced by the autocorrelation length. I mean, we did not adjust very much parameters that are just two realizations of the situation. But in any case, we get this very nice drop, and that is nothing than changes of the autocorrelation length. Okay, so that is somehow a traditional way for doing it. Here with the example of the estimation of the correlation dimension. And we also have been thinking on that, how to avoid this very complicated pre-processing procedure, adjusting several parameters and without knowing whether the whole thing which we did is on a good quality or not. And so what we thought is somehow summarized in the next slide. So the Fourier transform is a bijective transform. So the information which is contained in the time series will be contained in the Fourier transform. And the Fourier transform is characterized by amplitudes and the phases. And the Wiener-Khinchin theoretical correlation theorem, and a special case of the correlation theorem is the Wiener-Khinchin theorem, which means that the Fourier transform of the autocorrelation of a signal is just the power spectrum, just the amplitude square, right? But that means that in the sequence of the amplitudes, or the sequence of the amplitudes contain linear properties. And linear properties do not have anything to do with determinism, with nonlinear dynamics or something like that. For any kind of power spectrum, we can produce noise, right? And noise is certainly not deterministic. So the interesting property is somehow encoded in the sequence of phases, or it might be so that there is a non-trivial relationship between amplitude and phases. But there should be the interesting information content, right? And we have two numerical experiments in order to illustrate the information content in the Fourier phases. So what we can see here are the signals of an acoustic signals. Somebody is telling us an English phrase. We can.
Fourier phases are important quantities, although they are rarely considered in the literature.
So that is a phrase in English. And now we did two things. We did the Fourier transform, and in one procedure, we put it all Fourier amplitudes to a constant. So we destroyed all linear autocorrelations in the signal, but did not touch the phases. And in the second procedure, we didn't touch the amplitudes and replaced the phases by random numbers uniformly distributed between 0 and 2 pi. So what if we conserve the autocorrelations? Oops. That is noise. What we could expect. I mean, there's no noise with the same autocorrelations than the original signal. If we conserve just the Fourier phases, we are able to understand the message, right? Another example will be this photograph. So we have a photograph from this beautiful horse and this watch. And then we made a Fourier transform, exchanged phases and amplitudes, and retransform. So what we can see here, that are the Fourier phases from the watch and the amplitudes of the horse, and vice versa over there. And you can see where the important information is somehow encoded, right? Phases are important and interesting quantities, but possibly it is not that trivial to extract the information from the phase spectra. So we have here two examples. That is the example of the Rössler system and an example of the Lorentz system. The power spectra over in a semi-logarithmic scale. So that is here the dominant frequency of the Rössler system, and here we can see the phase spectra, the corresponding phase spectra. It seems quite noisy. It seems that it's not that trivial to extract information from this. But it should be there. I mean, mathematics does not lie. The Wiener-Kinch theorem tells us there is the interesting information. So how to extract, and that is just one proposal which I'm doing just now. I believe one can have much better ideas than what I'm going to present now. It's just the first shot, and maybe you have much better ideas, and please let me know afterwards. So what we did first, I would like to tell the bivariate case. So let's suppose that we have two time series, maybe two electrodes of an electroencephalogram or whatever. And so we make the Fourier transform. We have the amplitudes and the phases as a function of the Fourier frequencies, and thus we have two sequences of Fourier phases from the first up to the Nyquist frequency, right? From the first signal, from the second signal. And now we can imagine that these are two-dimensional vectors, right? In a plane between 0 to pi, 0 to pi. That will have, give some dots, right? Maybe that is the dot for the first frequency, for the second, third, and so on. But the point is that, of course, that is not a plane, that is a torus, because 0 and 2 pi points in the same direction. So in principle, these are dots on a torus. There is some small animal living on this torus, on this donut, may jump from one position to another, right? And this world is this torus. And we can see that here. And now the idea is to evaluate if there are correlations in this walk of this small animal on this donut, right? And then we define the distance between two dots by the shortest connection between them, as usual, right? I mean, there are several possibilities. In principle, infinite possibilities to go from one dot to another. There's just one possibility in blue is drawn over there. You may turn around and so on. In principle, there are 9 possibilities to make a straight line between those dots that is somehow visualized in this graph over there. And we are always taking on this plane, on this torus plane, the shortest distance. And then we are interested in changes of the direction. In changes of the direction, we have here Euclidean distances, and we are able to calculate the angle. And then we are estimating from those angles this J measure. It is called J because my small daughter is called Johanna, and so and she is quite inspiring. So that is the way we try to evaluate correlations on this walk on the torus, right? That is the idea. And we would like to well, anyway, we will get some number again, right? We give numbers to the computer. He will give us numbers, and we could draw a curve being happy. We need a significance level, right? And there now, it is a really great advantage that we are leaving out all this amplitude stuff. What we are doing now is just a random walk on the torus. And the number of steps, we adjust to the number of steps from the original data. And we do that n times. And if the estimates for the J of the original signal is below that of the n surrogates, well, then the results are significant on a 1/n percentage, right? Do I make myself understandable? I mean, if you have always the same angle, the measure is 0. That would be highly correlated, of course, very regular. No. If any deviation angle is possible, then this sum is equal to 0 and J is equal to 1. That would be expected for noise, right? So we create n random walks, noise walks over the torus, and then we get out such a curve as a function of the length of my time series, number of steps. And then I have to look if my estimates are below. And then I have a 1/n significance, right? The great advantage from that is that you do not have to create any more surrogate data. I mean, all these iteration steps, and it works or does not work, I have to make it again. And that for each time window, if I have to analyze, let's say, a sleep recording, EEG recording over the whole night, 8 hours, for each segment, I have to create surrogate data and surrogate data in order to estimate the significance of my results. That's no more necessary. I can do it once, and this curve is correct for any kind of data, for EEG data or seismic data or financial data or whatever. I mean, there's no influence of any kind of linear correlations. We are just looking for Fourier phases. So all the delicate issues in creating surrogate data are avoided, and the computer costs are also quite reduced. That is the way we are going to fix the significance level of our result. And now let's have a look to some results. What we can see here above, each of those dots that are the results for the Rössler system, and we adjusted the parameters that the Rössler system has a regular dynamic with a period 1. That is this dot over there. Period 2, etc. And then we are increasing, we are varying this constant. We are changing the dynamics of the Rössler system. All those dots here are representing regular dynamics with increasing periodicity. And these three dots are for chaotic dynamics of the Rössler system with increasing Lyapunov exponent, because the Lyapunov exponent is drawn with this black line. It's quite parallel to the Lyapunov exponent. We have the same here for the Lorentz system, that are dots for the regular dynamics. Again, red curve for the J measure, black curve for the Lyapunov exponent. This yellow stripe over there, if the results are above, then they wouldn't be significant. All those results here which are below, they are significant. That is the Hannon map. We can see here the parameter is changed such that we are changing between regular and chaotic dynamics. Again, represented by the Lyapunov exponent, and the red curve is the J measure. And I would like to emphasize, we are not adjusting any kind of parameter. We are just doing a Fourier transform, and that's it, and looking for the random walk. There's no parameter, no phase-space reconstruction, nothing. And then we could do the same thing. In a univariate case, we could just create two signals. One is the signal, and the other one with a time lag, right? Then we could do the same. And that is shown here. That is for the logistic map. Again, in black is the Lyapunov exponent, in red curves the J measure, and that is the bifurcation diagram here. And then, I don't know, violet, no, maybe a rosa or something, pink. That is a bifurcation diagram of the logistic map. And again, we are somehow mimicking the Lyapunov exponent, although it is different. The Lyapunov exponent is a limited measure. It's variable independent. If I'm estimating that from the X or Y variable, or no, reconstructing phase space, the results are the same. That is not the case for the J measure. The J measure depends on the time series. And we can see here, these are results for the Rössler, again, Rössler system, and the Lorentz system. The stripe over there indicates non-significant results. And the green curve are the estimates of the J for the X component of the Rössler system, and this violet one or blue one for the Z component. And we can see the period of this X and Y component just reflected in this oscillations of the results over there for the X component as a function of the delay, right? That is a delay over there. However, on the average, it is constant, right? It does not depend on the delay, not very crucial. That is for chaotic dynamics, the same for regular dynamics. And here again, for the Lorentz system, chaotic dynamics, regular dynamics, these dots here, that is just the jumps which is going from one ear of the Lorentz attractor to another one, jumping back, and then these bumps occur over there. That are just these changes from one side to the other side of the Lorentz attractor. Okay, what about noise? Noise is poison, right? And if you would like to analyze biological systems, empirical data, it would be nice if it is somehow robust against noise. Again, on the left-hand side, results for the Rössler, on the right-hand side for the Lorentz system, chaotic regime and regular regime on both sides. And that is the signal-to-noise ratio. We put a lot of noise on this data, and we can see there is some dependence, at least for the regular estimates over there, but it stays at very low values. It's quite robust. In black, again, the collapse of the Lyapunov exponent for the same signal-to-noise ratio. So it is robust to noise, at least much more robust than we could expect for the Lyapunov exponent over there, right? So that is somehow the part with artificial data derived from dynamical systems, well controlled. What about to some application to the real world data? I will show just 2 examples, and then I'm finishing. So what we can see here above and below, that are intracranial electrodes of an epileptic patient. They are just located within the epileptic zone, within the seizure onset zone. With this vertical line, seizure onset and offset are indicated. And what we did here is a double running window approach. So we have some time segment, which we are moving along the recording. For each time, we have a sequence of Fourier phases, but then we can do the random walk just for a subset. Well, we can have a frequency window, and we are moving the frequency window below from low frequencies to high frequencies. And for each of that, we get an outcome for the J measure, and we can compare that with our universal curve if it is significant or not. Again, all those results where it is not significant are indicated in red color. And blue, white, and red are the significant results. And we can see that in particular, in the post-seizure period, we get some dynamics. If we are able to compare that with the outcome of the dynamical systems we saw beforehand, that should be regular dynamics over there, right? You also can see here some dots. Well, I haven't said. That is a univariate application of the first electrode, the univariate application of the second electrode, and that is the bivariate estimate, which you can see in the center and the panel C. So we are able to indicate these kind of activity where we get some deterministic structure. And I asked the neurophysiologists that these are data that stem from Cuba, from Colombia, sorry, from a friend of mine over there. And he was revisiting this data and said, yeah, there is something very strange. I didn't take care about it because the real attack is over there. So I was not that interested by what happened some minutes before. But he said that it seems that the brain would go to the seizure more or less at this period, but does not succeed. And the referee of this work said, well, that is very surprising because you can see here large amplitude, slow oscillations over there. And that is very indicative for the epileptic seizure, but you are not detecting anything. And afterwards, where the activity is very small, the small power, there you are claiming you're detecting something. And our answer to him was, well, that's true, but I think that is an advantage that we are able to make visible things which are not visible by eye revision. I mean, the amplitude changes are just, I can calculate the power spectrum, or just looking through the signal, I see that the total power over there is much larger than after seizure. And our measures are not sensitive to that. We are not sensitive to changes of the power spectrum. And so we did some magnification of this part over there. That is drawn here as the signal, that is the power spectrum. That is the distribution of phases of this segment. And that is the distribution of the deviation angles over the torus. And we can see there is some small correlation over there, but this figure is very much alike if you have a random walk upon the torus, because that reflects the topology of the torus. If this small animal would run upon a sphere, there would no preference for certain angles. So that is a pure random walk, which you can see here. So and this here is a magnification of this post-seizure period here, where we can see this very red region. Again, the power spectrum. That are the Fourier phases as a function of the frequency and the deviation angles over there. So that is really different from that what we can see on the left-hand side. And that is what we detect over there. That's where we are sensitive for. I'm not declaring that the activity over there is pure noise or random, but it is clear that we are not detecting some deterministic structure. That's it, on the 1% significance level. With Bonferroni, actually, because we have several windows for each of the time segments. So that is one example. Another example which we put into the publication is where we have density variation of sediments of a paleo lake in Tlaxcala in Mexico City. And Tlaxcala is just in the neighborhood of the Popocatépetl, and they analyzed, I don't know, 2 or 3 meters of a block they extracted from a mine where I think 2.6 million years ago there was a lake, and just on a few kilometers aside the Popocatépetl, and so there have been eruptions and sediments are coming from this volcanic activity, and they caused damage, of course, to these biotoms within the lake. They were killed, and we can see here that this black stripes are just sediments from the volcanic activity, and this white regions over there that are sediments from biotoms within the lake. So that is the sequence of density variations. I think they have a resolution of a third of a centimeter or something like that, where they scanned this block of several meters. That is just one part of the data. Again, the white stripe, yellow stripe above indicates non-significant results, and the green and red curve indicate the results obtained for the J measure. We have been in contact with the specialist analyzing this data, a biologist, and she was quite happy about these results because they indicate something special. I cannot repeat it because I don't know the biology of that. I'm not a specialist on that, but according to her, these very pronounced minima over there indicate something special what happened in this 2.6 million years ago in this sediment. So that is everything I wanted to tell you. Thank you very much for paying attention, being here in this extra session. Thanks a lot.
Well, thank you very much, Marcus, for the nice talk. Is there any question? No? Well, I have.
Thank you. It was really interesting. Sometimes in this time series, you discretize.
Discretize,
You have a time discretization, because I mean, the
in which
Fourier
figure? The phases?
No. I mean, in general, you can discretize just by changing the let's say the time periods.
This one.
Yeah. So the question is, just your method is sensitive to the discretization. So what happens if you increase the?
But that is not a. We adjusted the parameters of the Rössler system. Let's say this dot, such that we have period 1 dynamics, right? Created a time series and did the analysis, and the result was this dot. In principle, this line is confusing because in principle there are only these dots. Then we adjusted the same system with parameters. That is period 2. I think that is period 4. I don't remember. So we are changing. Let's say, I don't know whether complexity is a good word in this context, but we are changing qualitatively the regular dynamics of the Rössler system. And what we can see is that the J measure increases successively. We can see somehow I don't know how to call it, degree of irregularity of the regular dynamics. Or,
Okay, thanks.
Another question? Anybody? No? Well, I have another question, Marcus. In your last slide.
with the sediments. That's my weakest point.
No, another, the other.
The other, thank you.
Yeah. What is the meaning of that index
Physiologically,
physiological? I mean,
I'm a poor physicist.
you get a very impressive result, but what is the meaning of? Because
If you're asking me what that means physiologically, I have to give an honest answer. I don't know. It's somehow like a reset. That is possibly a way you can look to that. I mean, there is this very drastic event over there, and there's some kind of reset what occurs. And talking with neurophysiologists, that is temporal lobe epilepsy, that are electrodes which are implanted in the hippocampus, and this kind of epilepsy is something like there is a period where they are where the sequence of seizures is comparably diluted. So the intervals between seizures are larger. And then there are intervals where there's coming one seizure after another. It's something like there is some kind of, I don't know, pressure in the brain, which is, and then it bursts. There's some bursting. And this bursting are this high frequency of different seizures which occur, maybe in between 1 or 2 days. They are puff, 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 puff. And then again, it gets calmer in some sense. With this respect, that is maybe something like a reset, a slowing down of some activity, provoking seizure. It's kind of a refractory period or something like that.
okay, thank you very much. Well, if there is no question, we can finish this minute. Okay, thank you very much. Marcus,
Thanks a lot. Thank you very much.
Switch off the